Good afternoon or good morning, folks, and welcome to the presentation on the Madden-Julian Oscillation by Jon Gottschalck, the Operations Branch Chief at the Climate Prediction Center. This presentation will be recorded and available for later viewing. We will be taking questions. We ask that you put your questions in the chat panel, and we'll address those at the end of the presentation. Jon's been at CPC since the early 2000s. We met many years ago when he, with a few others, brought Madden-Julian Oscillation concepts into the forecast realm at CPC, and his research and operational techniques have improved over time. We've seen a commensurate increase in the skill of forecasts related to that, and that's what we're going to learn today, is that what happens in the tropics can affect us here in the mid-latitudes. And with that, Jon, I'll pass it on to you.
Okay, thank you very much, Ray. I appreciate it. Hopefully everyone can hear me fine. Yes, as Ray mentioned, my name is Jon Gottschalck. I've been at the Climate Prediction Center since about 2004 or so, and I'll be giving kind of an overview, as a lot of information as best I can on the Madden-Julian Oscillation from an operational monitoring, prediction, and impacts perspective. And so the outline of what I plan to go through this afternoon or morning is just an overview of the characteristics and the general structure of the MJO, how we monitor it, and assess its status or strength. The general prediction skill that we currently have with forecasting the MJO through the tropics. We'll spend quite a bit of time on tropical and extratropical impacts and how you want to try to utilize or assess those for situational awareness for both, again, as I mentioned, for both the tropics and linkages to the extratropics, and then wrap up with a couple slides on our weekly assessments from CPC. So the first section shown here, just characteristics in general, and again, I know there's probably a large range or spectrum of folks that are quite familiar with the MJO, and others who may not be very familiar at all. And so I will go through the best I can, kind of summarizing some of the basics in the beginning here. So characteristics of the MJO. One, the MJO is a what we call an interseasonal wave or fluctuation or disturbance, depending on whatever you want to call it, that's originating in the tropics. And it's interseasonal because its time scale to move around the globe, which I'll show in a second, it'll become a little bit more easier to understand, is within 90 days or within a season or interseasonal. The MJO results in many changes to atmospheric and oceanic variables. Some of them are listed there, but there's quite a few that we'll go through during the webinar today. The typical period of the MJO cycle, and again, that's for this disturbance to circumnavigate the globe, if you will, through the tropics, is typically 30 to 60 days. Some are on the faster end, closer to 30 days, and sometimes even more quickly than that, with a shorter period. Some extend more towards that longer range, towards 60 days. It varies. That's just a typical range. Also, the MJO acts on a global spatial scale, which makes it very interesting and important, but also very difficult and challenging in forecasting and also relating its potential impacts. And what makes the MJO even more interesting, but also a challenge, is that this wave or disturbance, as I mentioned, coherently propagates eastward in the tropics, more slowly in the eastern hemisphere, then a little bit more quickly in the western hemisphere. So I know this might be delayed through the web, but this is an animation of precipitation that's filtered for the MJO, and there's a number of different things I want folks to take from this. First, this is a visual representation of what the MJO is at its essence. The blue shades indicate enhanced rainfall, the red shades indicate suppressed rainfall. And the main things you want to know, if you're starting about now, let's say, at least on my screen, you'll notice the blue shades start in the Indian Ocean. They'll move across the maritime continent or Indonesia region into the Pacific, and then reemerge back in the Indian Ocean. And it'll take about 48 days on that clock, if you will, in the upper right, for that to happen. And what's important beyond that is that right behind that area, or with those blue shades, you'll notice the red shades are right behind it. So this is dipole, or couplet, if you will, of enhanced and suppressed tropical rainfall in this particular example that moves around the globe somewhere on the order of about, on average, 45 days, so between 30 and 60 days. The next thing that's important from this animation to take from it is that these are large-scale enhanced areas of tropical rainfall. We're not talking about mesoscale type systems or diurnal activity. This is very large scale, the size of ocean basins, or small continents or sections of continents and so on, over that 45-day period. And so you can kind of see how this changes and moves across the global tropics. Now, if we take a look at that now from more of a vertical structure, and I'm going to focus just on the, if I can look the pointer here, the probably just letter H, just to kind of show things. That blue area that I showed in the previous slide, think of this cloud as that cartoon here as that large area of upper level motion, and therefore large scale convection. What you'll notice at that point is that you have low level convergence indicated by the green arrows here, and upper level divergence basically at the upper levels is indicated by the arrows on the top of this area here. So it's a baroclinic disturbance. What's indicated by the blue and red shades are deviations in sea level pressure. So what you'll see is the enhanced phase, a lowering of pressure, enhanced rainfall, and then behind it, as you'll notice, as this moves out to the east, as I showed in the previous slide, you'll have suppressed convection or downward motion behind it, and higher pressure as indicated by these green arrows down in some of the lower rows in this particular plot. On the bottom, on the x-axis here, if you will, is just kind of the longitude of where this typically happens. And what you'll notice is that the convective tropical rainfall signal is very much confined or most pronounced in the Indian Ocean, Indo-Pacific area, Indian Ocean, Indonesia, and the Western Pacific. Tends to die out from a convective point of view, but is maintained in the circulation. And it's that circulation that transverses the entire tropics and will result in other areas of enhanced rainfall or suppressed rainfall across parts of South America, Central America, the monsoon regions, the Atlantic, and then eventually the Africa region. And then once it gets back into the Indian Ocean, it becomes more widespread convective-wise overall. And so we group these various areas of large-scale tropical rainfall into phases, and we'll talk more about that. On this particular slide, this is a three-dimensional structure of the MJO. So again, think about those blue shades and that animation as this thunderstorm cloud or cartoon here. So we have very large upward ascent in the main area, which would be the enhanced phase of the MJO. Change my of the MJO. You notice at the lower level, which is the 850 millibar plane, so closer to the surface, you'll see these enhanced easterlies here, and then enhanced westerlies within the area of enhanced convection. At the upper levels, you'll see, as I mentioned, divergence aloft, as indicated by these arrows. And what's important about this particular figure, which is why I show it three-dimensionally, is that one of the most important features of the MJO is that the development, based on this wind structure, in the upper levels, you'll develop anticyclonic gyres or circulations that are symmetric about the equator, north and south of the area of enhanced convection. And at the surface, you'll have cyclonic gyres or cyclonic circulations that develop based on some of the wind field in the, again, symmetric about the equator. We'll show this a little bit more in a second as well. And these are very important because they result or contribute to a lot of the impacts that we see moving forward in the later slides of the presentation. But these are very important, distributing mass and momentum throughout the atmosphere from both the tropics into the mid-latitudes and and higher latitudes. So this is a actual composite of rainfall data to kind of illustrate this in one more way. The green areas are enhanced rainfall, brown areas suppressed rainfall, and these are different phases, which I'll explain what those are as we move forward, but they're key to where the enhanced area convection is, which is indicated by the green here. And the reason I want to just show this is, again, that over time, again, over about 45 days on average, this enhanced rainfall from the enhanced phase of the MJO will shift eastward with time, pick up speed typically, become a little bit less defined with respect to convection as it gets into the Western Hemisphere. And then behind that, you'll notice suppressed convection that comes in behind it, or the brown shades, meaning below normal rainfall, and suppressed large-scale subsidence behind it as you go through. So this couplet is what moves eastward and around the global tropics in about 45 days. Okay, so those are the general characteristics. As far as how we monitor and assess, there's a number of different things. What I want to show now is an animation that, again, I'm not sure how it will come across through the network, but this will be available to everyone who is interested in it offline. But what I'm going to show you is upper level velocity potential, which is just basically a proxy for upper level divergence, let's say, and shows the enhanced and suppressed phase. And what you'll see are kind of a mixture of green and brown contours, not very organized at the beginning in February, and then it'll organize itself into half the globe in green and half the globe in brown, which is kind of that wave one structure of the MJO that you'll see typically with good mature MJO events. And then as we get back further into May, you'll notice that it becomes more disorganized again. So I'll go ahead and play that now. And so depending on where you're on the animation, you'll see that. In the beginning of February and March, there'll be kind of mixtures of browns and greens, not very organized. But as you get into late March and April, you'll notice the shades become much deeper, darker, and you have half the globe in one of the colors or shades, if you will, and the other half in the other, and it'll propagate coherently to the east. And then as you get into June, you'll start to see again a little bit more disorganized behavior, meaning the weakening of the MJO. And so again, I'll let that run one more time, at least on my machine here, and for folks who can see it. And as again, the strongest point of this MJO event was during the month of April into very early May. And then it'll basically weaken as it gets into late May and into June. So another way that we monitor the MJO because of this eastward propagation is through what we call time longitude diagrams. And time longitude diagrams, in this particular example, time increases as you go downward. So this is a period from 2007 to 2008. Longitude is on the x-axis here. And what's shown is an average of OLR anomalies. Red shades indicate suppressed rainfall, let's say, and blue shades enhanced rainfall. And this is average between 5 north and 5 south. So it's basically when you see this propagation eastward, this tilting down to the right, for example, is indicated here by the blue, and then you have the in this area here the green. I'm sorry, the warmer shades, and then followed by the blue shades again. They're tilting down and to the right, and that's because that's a signature in these diagrams for eastward propagation. Because as you increase in time downward, you're moving further to the east, from say the Indian Ocean to Indonesia to the Western Pacific over time. And so that's one thing. You'll notice here that these are alternating periods of dry conditions up the top, but then wet is indicated by the blue, dry, wet, and then again dry here at the very end in January of 2008. But what's very interesting, so that sort of signature is very indicative of the MJO, meaning subseasonal variability or interseasonal variability. What's very interesting is what happened after that in this purple box. You'll notice that these anomalies become much more vertically oriented in these diagrams, which means these areas of enhanced and suppressed convection are generally persistent or stationary. And that's this particular period is when the La Niña conditions developed in during the month of February in 2008, finally developed across that area. The MJO stopped, meaning this this variability here stopped, and this became more of an ENSO sort of signature in this particular diagram. Real quickly, low-level winds, this is just some actual data from the low levels that shows from an MJO event where we have the blue box enhanced easterlies and the red box enhanced westerlies, if you look at the arrows in this particular case. And the black oval is basically indicative of where that enhanced phase or the enhanced convective phase of the MJO would be located. And you have very strong low-level convergence in this area of the in the black circle, for example. At the upper levels, very similar again. You'll notice very strong upper level westerly anomalies out ahead of this convection, where the enhanced phase is basically in here. And what's very important to notice, and this is actual data, not that schematic necessarily, theoretically, you'll notice these very strong atmospheric and cyclonic circulations north and south of the equator, and cyclonic ones out ahead of it in the upper levels. And at the surface, you would see cyclonic circulations north and south of this area of enhanced convection as well. And these are very strong, again, as I mentioned, very important for impacts that we'll talk about later on. Now, this is another set of diagrams. This is from the Dynamo field campaign from 2011 to 2012, which really was a great period for MJO activity. It was a field campaign to understand better the MJO initiation and decay processes. And on the right-hand side, I won't go into too much detail other than to show this is the same sort of diagram, time longitude down, where you have increasing time this way. And so the dashed and dotted lines indicate MJO activity. For example, here's a period in basically October and November into early December where the MJO was very active, but you'll notice the lines are pretty more oriented, more horizontally, indicating faster movement. And on the later period down in here on the bottom part of the plot, you'll notice that this is a more organized, typical MJO longer period event where you can see it takes slope is a little bit less, a little bit more vertical or down to the right, and also more wide, if you will, in the anomalies compared to say something like this, which is very more short, if you will, smaller in time than say something like this. And on the left-hand side, it's interesting is the specific humidity vertically, and you can see during that first period, what we call Dynamo period 1, the gradual moistening of conditions in the lower levels that eventually led to deep convection. The drying periods were not as intense during this particular period, and you can see the rapid enhanced phases move through this particular area. This is a box, is indicated by the double lines here, 10 north to 10 south, and 75 to 85 east. But the character of the MJO after that, for this last event, was very different. You could see very strong period of suppressed or strong subsidence, and a little bit less in the way of enhanced convection, and a much longer period of ramp up of the enhanced phase, and over this longer period of time. So the character can be very different. As far as tracking the MJO can be very complicated due to all the variables that I just mentioned. And so we try to use indices to kind of scale down and track the MJO, similar to ENSO, for example, with Niño 3.4 and so on. And one of them that was very often used is the real-time multivariate MJO index, or RMM index, that I think most people are familiar with, from Matt Wheeler and Carrie Hendon back in 2004. And what's shown typically in this particular example is what's shown on this left-hand plot here is the MJO activity represented with this MJO index in phase space for the event at the exact same time as shown here on the right, that we kind of just went through the last couple slides with respect to how you would, how the MJO looks in these time longitude plots. In this particular case, it's velocity potential, where the enhanced phase is the blue and green shades, and the suppressed phase is the brown shades. But in this particular plot to the left, the different phases, as I mentioned, are for the enhanced phase or enhanced convective nature of it. And phases 2 and 3 are the Indian Ocean, for example, down here. phases 4 and 5 are across Indonesia, and the Western Pacific are across 6 and 7, for example, and then later on phases 8 and 1 for the Western Hemisphere in Africa. Now, each one of these points is a daily value of this index, which is utilizing 850, 200 zonal winds, and OLR. I won't go into the details of how it's actually produced, but basically the farther you are away from this inner circle, the stronger the projection or the stronger the MJO is in this particular index. And you'll notice these points, as you increase each date, go in this counterclockwise movement. And so this counterclockwise movement in these phase diagrams is a signature for eastward propagation, right? Because you're going from the Indian Ocean, let's say, for example, and as you increase the day, you go ending up into the Western Pacific, for example. And you'll notice in this plot here on the right, you have very good, strong anomalies. And then all of a sudden, about May 1st or so, you start to notice very nondescript or weak signals down through here. And that's exactly what you see in this index as well. Strong MJO activity, projection, and then all of a sudden it starts to head towards the circle, meaning the MJO is weakening, and it's also not moving east anymore. It's actually going directly towards the circle. So this part right here is very clearly, in this particular manifestation or plot, showing that the MJO is weakening in amplitude and is also no longer propagating to the east. And the last thing I want to talk about is that the MJO is made up of a lot of different disturbances within it, and I don't have time to go into it here. But there are higher frequency variability that can be monitored and predicted, such as atmospheric Kelvin waves, equatorial Rossby waves, and it's all these features that move west, east at faster and slower speeds, at different temporal scales, and so on, that make up this MJO envelope. Okay, and it's this envelope is what moves east in time that I'm referring to. For example, if you look at this particular plot up here, you'll see areas of convection or blue shades, let's say, that are clearly moving faster than this overall envelope, which is what I'm referring to here. Some that are moving east, like that one, and then some are moving west, like this, which is an equatorial Rossby wave. And so it's all these sort of features that help to form the enhanced phase of the MJO. These are all different features embedded within the MJO envelope overall. And we'll talk more about that as a predictor for some other things for our hazard assessment in about a month. And before we move on to the prediction skill, the interannual variability of the MJO is quite large. And this is just an example from the Bureau of Meteorology in Australia, which shows kind of from 1974 through 2018 or into 2018, the variability of the MJO, where when you see gray areas like this, for example, higher variance. This is basically the 91-day running mean of the amplitude variance of the amplitude, and shows where the MJO is typically active over those 90 days. And you can see there's long periods of very weak activity, for example, in 2013 and 14, periods of very active activity. Overall, this is the dynamo period here, for example, in 2011, 2012, which happened to be a very good period after a very long period of a couple of years of generally weak activity. Also, some of these events are known to really peak up before El Nino events, such as before the 96, 97, I'm sorry, the 97, 98 El Nino event. The MJO activity was quite enhanced, for example, in that period. Okay, so moving on to how we predict the MJO is that the forecast skill depends a lot, obviously, on the method and the metric used, but the best forecast skill right now has really improved quite a bit and has mainly from the dynamical model forecast and from some centers. And they have extended out the forecast skill, usable forecast skill, as we would define it as, say, 0.5 anomaly correlations, to as high as almost 35 days now. There's both statistical and dynamical model predictions are available, and the dynamical model forecasts have really caught up and have become quite good in some areas. Now, again, this is just predicting the MJO itself in the tropics. It's not saying anything about the teleconnection to the higher latitudes. However, still, a considerable portion of the skill does come from established ongoing events. We still have problems with the transitions in many ways with respect to when the MJO really develops or the onset, and also when it decays. We've gotten a lot better with the dynamical models in showing that to us than, say, 10 years ago or even 8 or 5 years ago. But basically, there's still a challenge there that we're still learning about, and some of the efforts during the Dynamo campaign, or hopefully we'll be getting into some of the dynamical models at this point and moving forward. So quick review, kind of the baseline of some of the early statistical forecasts that we used to have, and you can see that skill is quite low. You take a look at the plot on the left, the persistence, which is the kind of the dashed line. Really, we had, and this is forecasting the RMM index, for example. So it's kind of a wave one forecast of the MJO, not necessarily convection. The convection forecast skill is considerably less, as one would expect. But in general, forecasting of the RMM index from these statistical methods are pretty limited. This is from a paper for 10 years ago now, 10 years old at this point, that really only extended the prediction out to about 15 days, 16 days, using a linear regression technique as one method. But when you go to some of the more recent papers in 2014, for example, 2013, and more recent, and these are examples of prediction skill from the CFS and the European Sentinel models that go out beyond 2 weeks, for example, and the prediction skill is quite good, has improved quite a bit. And the upper left, for example, is the European in red and the CFS in blue for the RMM index for both the two different RMM1 and RMM2, for example. And you can see this has improved quite a bit from what I showed in the previous plot. At this time, the CFS was about 20 days, 21 days, and the European was on the order of as much as 25, 26 days when you average those out. Above is the CFS variation that shows one thing I want to mention as well. The forecast skill varies by, like most things, as a part of the seasonal cycle. Highest skills during the winter, as you can see, if you just follow this 0.5 or 0.6 line, for example, you can see during January and February, forecast skill after that level of anomaly correlation. 18 days decreases to about 13 or 14 days at this time. During the summer, that increases. This is pretty typical of most of the models and most phenomena, actually. And what's shown in the lower left, I won't really go into, is just the improvement in the European model of the RMM index over time, over the last 10 years, 12 years at that time, through 2014, of various levels, 0.5, 0.6, and 0.8. And you can see that there's been quite a bit of improvement. More recent results from the S2S database, from the various models that are shown here. The main takeaway here is that the top plot is just all seasons for the reforecast from 1999 2010, and you could see the various models there. But one model, the European model, as indicated by the dotted blue lines, is considerably above some of the rest. And if you look at that, it's been further improvements from what I showed on the previous plot, and that by the time we get to 0.6 anomaly correlation, we're on the order of about almost 35 days. And the bottom plot is similar, except it's just for the December through March period. And what you'll notice, not so much with the European forecast, but in general, the envelope of all the model forecasts shifts up a little bit. So as I mentioned, the prediction skill in this particular index is generally higher during the winter months, say November through March in general. Now, at CPC, we have had an activity where we've basically taken the RMM index methodology and applied it in real time to model forecast data. And what's shown as an example here, we're in the process of upgrading our MJO pages and our models and so on. So these are a little bit older plots for some of these forecasts, but which shows we applied it to various number of models of GFS, of course, the Canadian, European, JMA, and others. And we have a page for that. And the point of showing these plots is that we have dynamic predictions of that index, which gives us a general idea of the ensemble spread for confidence, how strong the MJO may be from the model perspective, amplitude, and how fast it may be going in which phases. And so as I mentioned, we're in the process of updating the model forecasts on this page and adding new models that extend further out in time. For example, the GFS runs that go out to 30 days now and so on. And we'll talk more about some of these tools when we do the GTH webinar in a month. One last thing I wanted to show is that the skill I showed varies with respect to season, but it also varies with respect to the initial phase. And that dependence is also a function of each model. And for example, if you take a look at, this is from results that I did here at CPC for a few years ago now, with the NSEP model, which showed higher skill when the MJO was at a current initial state in the Western Pacific phases, let's say 5, 6, and 7, and lower, as you indicate, like for example, if we take a look at the 0.5 anomaly correlation, 10 days for phases 1, 2, and 3, and then it goes up. So there's more predictability in the more Western Pacific region for that model. Whereas for the Canadian model with that real-time data, kind of the opposite. It did perform better in the Indian Ocean and western parts of Indonesia than per se that it did in some of the Western Hemisphere areas. And the point of this is that you can use this independent information to develop a multi-model ensemble forecast of this indices which we're working on, and you can get a better result overall, similar to many other applications as folks are aware. So moving on to tropical and extropical impacts now. I've already talked quite a bit about the changes in rainfall with respect to the MJO. As you could see, both I've shown the winter previously, but they also have different character in the summer, boreal summer, for example. One thing you'll notice in the wintertime, and again, these phases that are shown here are the RMM phases that I showed earlier. And so what you'll notice is more zonally oriented with propagation over time. And so some hot spots that during the winter, for example, for enhanced precipitation, let's just focus on that for simplicity, are very often across parts of Northeast Brazil, parts of Eastern Africa, and of course, as I mentioned, the main convective areas across the Indian and Western Pacific Ocean, as well as Indonesia. And you can kind of see that as you go out in time. This sort of signature is very, very clear. Now, as you go into the summer, however, what you'll notice is that there's as much northward propagation as there is eastward propagation in the Eastern Hemisphere. So if you look at the enhanced phase of the green areas, let's say, in phase 2 and so on, you'll notice that they move east, but not quite as far, and they also move north into the Western Pacific and so on. And also, of course, through the seasonal cycle, the enhanced rainfall is also north of the equator, pretty far, and will impact parts, instead of South America, of course, will impact parts of Central America, the East Pacific ITCZ, and of course, the Atlantic Basin and the West African monsoon in time as well. So there's certain hot spots for both wet and dry conditions associated with the MJO that show up in these composites. Now, one of the main impacts also with the MJO is its impact on the low frequency or ENSO. And it's been shown through various studies and in real-time monitoring, the MJO can certainly modulate the intensity, timing, and duration of ENSO events. These impacts occur both at the surface and also at depth. And this is a nice example of how the MJO is modulating the increase in SST during an El Nino event a while back now, where you can see the black line is basically, sorry, the black arrow is a gradual increase of SSTs in the Niño 4 region and Niño 3.4 region associated with this El Nino event that developed during late 2004 and into 2005. But you also will notice this variation that's on the interseasonal timescale in the box related to the MJO. And they're not trivial changes. They're on the order of 0.2 to 0.3 degrees anomalies, and it can be very often can mislead people about potential ending or development of or strengthening of ENSO conditions, and they're definitely related to more of the MJO variability itself. And these are caused by changes in insolation, solar insolation, evaporation due to wind changes, and so on at the surface, in large part. Now, one of the things that's very important also that folks I know are very much aware of is that when there's a westerly, when there's an MJO event, the trade winds or the easterlies in the equatorial belt will weaken. Sometimes they'll even become westerly in the total field, and will cause the sea level height to rise in the Western Pacific and initiate what's called a downwelling oceanic Kelvin wave. And what's shown in this animation is basically warmer water from one of those waves that moves from the Western Pacific up the thermocline in the Eastern Pacific towards the surface. And depending on the series of these events, westerly wind bursts or more MJO related westerly anomalies, you can really make some large changes in the sea surface temperature pattern across the Pacific Basin over a period of 6 to 12 months, for example. And so the MJO can have a large, depending on the situation, sometimes it can make the difference between how an ENSO event evolves or strengthens or weakens over that several month period. One of the main impacts of the MJO that's been well known and documented by many studies is the impact on tropical cyclones. And this has been well known from the original kind of pioneering work by Maloney and Hartman in the early 2000s, which showed that during certain phases of the MJO, the likelihood of tropical cyclone development was either enhanced or degraded or lowered in probability. And this is a classic plot here on the left-hand side that shows that. At that time, they call it the westerly phase, but basically that's the enhanced phase of the MJO, and the suppressed phase would be down here, or the easterly wind phase. And you can see a pretty large difference. And these studies have been done for all the ocean basins multiple times, and they show very similar results. And so it's a pretty robust relationship. In one particular year, in 2008, for example, this was really matched up very well where we had MJO activity, where we had bursts of tropical cyclone development during that summer, as indicated by the red circles, and then lulls indicated by the yellow boxes, that really lined up very well with the MJO activity. And you can kind of see that in the background. Again, these are velocity potential anomalies in the time longitude format. So you can see MJO activity here before the season or in the early part of the season, and then very strongly during much of the season, during the main peak, and later into the early part of November, where this activity really matched up pretty well with these 2-week periods of active tropical cyclone development and then more suppressed conditions. And so it can be a real predictor out to multiple weeks, depending on how strong the MJO is and whether it maintains its integrity during multiple week periods. One other thing, the MJO also can affect the southwest monsoon or monsoons in general. But this is an example where I thought was interesting to show is that very often with the MJO, as I mentioned, the tropical rainfall in the East Pacific, the ITCZ in the Eastern Pacific will become enhanced. This is kind of an example of that shown here, for example. And generally, with the westerly winds that eventually will come with the MJO, you can generate more efficient cyclonic vorticity, and depending on the shear conditions over that general area, you tend to have potential more development of tropical cyclone activity. And even if you don't have development, this active convection may lead to moisture surges into some of the areas that are impacted by the monsoon, for example, the Gulf of California, and also from the Gulf of Mexico, depending on the situation. That can very lead to periods in which the monsoon can be very active or enhanced especially active for, say, 2 or 3 weeks at a time, depending on the situation. And this has been documented in a few studies. And so the idea of an enhanced East Pac ITCZ, tropical cyclone activity, takes time, but it gives you some potential lead time, predictive value at longer leads for hopefully enhanced monsoon, or in some other cases, the suppressed or a break in the monsoon. And this is shown nicely in this particular plot, which is the, sorry about these lines here, but basically this is from Australia monsoon, different time of the year, of course, but you can see very clearly the different phases of the enhanced MJO and suppressed MJO in this particular example. And in some of these areas where the rainy seasons are shorter, this can play a larger role in your seasonal total, whether your monsoon fails or not. And this is an example of that for, again, different part of the world. One other thing recently in the literature as well, from Pepin here, Philip, the development of, or the enhancement of the Central America gyre associated with MJO westerlies along the equator. We had sort of a similar sort of event with the systems that we had in the East Pacific, Central America disturbance, enhanced rainfall, and eventually what became Claudette from what's called a Central America gyre sort of circulation. And in the literature, in this particular study, a lot of these events were related to certain phases of the MJO, and this shows an example of that, where on the left-hand side, where the potential height and anomalies and wind vectors were particularly strong in MJO phases 8, 1, and 2, and then opposite for phases, MJO phases 3 through 7, for example, on the right-hand side. So that's another potential. We'll talk a little bit more about this as a predictor or an assessment of the global tropics hazards outlook as well next month. Now, moving towards the extratropics, a major thing, obviously, with respect similar to ENSO, is the idea of tropical heating associated with enhanced rainfall. This has been shown theoretically, as shown in the middle plot here, where you have a heating source in the form of enhanced rainfall or convection on a large scale, and you can generate dispersion and wave trains from the Pacific towards North America. This happens on multiple time scales. It happens with ENSO, of course, but also can happen with the MJO. And the MJO's impact to the mid-latitudes very much is related to that. And it's been shown, as I mentioned theoretically, as shown here in this middle plot, but also in various data sets from some of these references that show the enhanced, these blue areas here, for example, enhanced convection generating alternating patterns of high ridging and troughing that span north at first and then down basically across the U.S. And these circulations are very important for impacts, of course, to sensible weather across the U.S. And so, similar to ENSO, a lot of the largest changes are across the Pacific North America sector. These changes in mid-latitude circulation, again, as I mentioned, are very similar to ENSO, but act on a time scale of a couple of weeks as opposed to being evident in seasonal long-term averages. The strongest teleconnection, similar to ENSO, is typically during the late autumn into the spring, early spring. Some of the strongest MJO events and teleconnections to the U.S. occur in March, for example, February and March. And unfortunately, or as a forecast challenge, is that each MJO event, of course, occurs in a different season. ENSO state, background mean conditions or synoptic pattern, and the impact, therefore, in the higher latitudes can vary largely from event to event. It creates a major forecast challenge that we continue to work on. Also, the Rossby wave train response that I showed in the previous plot can certainly act to enhance or dampen the circulation at the time. And this forcing shifts eastward with time with the MJO as it shifts eastward itself. And so this this can be thought of in a similar way, but not quite as fast and as amplified as, say, for example, a recurving tropical cyclone from the Western Pacific into the North Pacific, and then later the dispersion downstream. But it's a similar sort of process. And it can be very difficult for the models, dynamical models, to properly handle that teleconnection. So there's a long way to go with respect to taking the increase in predictive skill from the MJO in the tropics that I showed to the impacts in the midder latitudes associated with that MJO activity. So we still have a long way to go there, but it is improving. What was shown here, the next two slides, one is kind of like, say, the peak or the most skillful or most coherent aspect of using MGO composites, which are for all the MGO events divided up by phase for the November, December, January period. This is a period from 1979 to about, I think, 2000, a few years ago. And it just shows some of the typical, on the left-hand side is the different phases and what the anomalies are, meaning warm shades warmer than normal. This is for temperature, sorry. And blue for below normal temperatures. But on the right-hand side, which is just as important, it's the significance. Now, this particular plot is kind of reversed in many ways from what you typically see, but you want to focus on the areas that are basically purple and maybe the dark blue, because, like, for example, the purple is 95% significant, for example. And so one of the strongest signals to point out is during November, December, and January is for above normal temperature in the eastern U.S. during phase 6, as you can see on the right-hand side, where we have very strong significance. The areas in which you have more of the red and yellow, those are not really statistically significant and should be used with very little extreme caution or not used at all. And an example of that would be some of these weak anomalies, for example, let's say here in the east for phase 7, where you kind of see those shades here on the right. So this is kind of from the upper limit sort of side of point of view of things. And then you go to precip during the summer. And what you'll notice is those areas of purple and blue where you have a lot more, where the signals are statistically significant, they decrease a lot. And that's not surprising. That's the same impact for precipitation in pretty much all time scales. But you can still have composites for this as well. And this is an example, again, for May, June, and July, and that's meant to be kind of at the period where the significance area on these maps and the anomalies in the composites are kind of at their minimum. So I try to choose two bookends for this particular example. On our webpage, we have composites for temperature and precipitation for all overlapping seasons for these phases for both temperature and precip. The other things that we have on our website that are important are lag composites. This is an example for RM phase 3, where the lag increases with time, and the lags are 5 days each. So lag 1, lag 2, lag 3, 4, and 5. This is basically typically what's observed from a composite analysis point of view on the order of about 25 days out in time from when the MJO index is in phase 3. In this particular case is the Eastern Indian Ocean. So it gives you a little bit of a predictive aspect to what the circulation may look like, again, from a composite perspective of all past MJO events and for various seasons, in this case, January, February, and March. One other thing that's important also is the MJO has impacts on some of the typical indices at the higher latitudes that we monitor very closely, like the PNA, the NAO, and so on. And this particular study, and there's been many others that have kind of confirmed this, is that we typically see very often with good MJO events during the wintertime, there can be a link between the tropical convection associated with the MJO and then with a certain lag. In this particular case, this is an example where study where a cluster analysis of 500 hectopascal heights across this domain is indicated here was applied, and there were 7 relatable patterns or clusters that came out of that. One of them, as most people will recognize very strongly, an NAO pattern here. In this particular case, negative NAO. And what's shown is on this side here is that there was a significant result in that the percent change in the occurrence frequency of that particular pattern, this pattern here, the negative NAO, did occur on the order of 40 days after MJO certain phases. So, for example, in phase 5, which again is convection in the eastern part of Indonesia or the maritime continent, there was a statistically significant, which is what's indicated by the colored bars, of on the order of almost 30 days lead time for a switch to an NAO or frequency of occurrence of this pattern. So basically a switch to the negative NAO from a positive value on the order of about 30 days. This obviously doesn't happen all the time with all MJO events, but this particular study showed that this was a statistically significant result. And there were other patterns similar to this for the PA that I don't have time to show that also indicated certain phases of the MJO had an elevated probability compared to climatology of switching to this pattern, which is what I'm trying to say. It's a potential shifts to some of these key teleconnection indices. And so kind of a summary real quick. This is a 300 hectopascal height wind anomaly map for November, December, January, and February. And I just like to kind of show this, some of the strongest signals during the winter time, just kind of in a nutshell. And that is that when the MJO is, these are basically instantaneous composites now, not lagged, that when the MJO is in phases 3 and 4, this ridge trough pattern across the Pacific during phases 3 and 4, as you can see, you'll recognize this from what I showed from the theoretical diagram and some of the empirical things where you had this kind of like arcing from the enhanced convection. And then this continues. And then one of the strongest signals, is, as I mentioned, is 5 and 6 MJO phases where you have a very strong southeast U.S. ridge. And one also important thing to notice is typically during phases 1 and 2, during the winter, again, you have very strong or enhanced subtropical jets, first across the Pacific and then along the southern tier, for example, similar in many ways to El Niño events. And you can kind of see that here with the black arrow, for example, in the composite for this particular. These are 300 height 300 height and wind anomalies for those particular months. One thing that's also showed, which I think most people are aware of during basically January and December, when the MJO is active, there's a much more higher probability of potential heavy rainfall events. Or in this particular case, this is from a paper where they documented flood day probability, and that you can see the greatest likelihood of those occurring during those months was when the MJO is in phases 6 and 7, for example, 6 especially, of course, and that's when the convection is further east in the Pacific, more able to be tapped by any sort of troughing or circulations in the mid and subtropics. What's also shown was with respect to severe weather, there's a lot of variability in the relationship, the results, and the conclusions. Some studies have found, as indicated here by Thompson and Roundy, that there's actually an increase in what he termed violent tornado days for MJO phase 2. There's been other studies as indicated down here, listed down here, that also indicated a relationship for certain phases of the MJO for hail currents and so forth. But also other studies have refuted that. For example, Tippett's 2018 study kind of showed that those results may not be conclusive, and there's quite a bit of variability by phase. And this middle plot just kind of shows what the circulation is at 300 hectopascal for heights and winds for this particular period. And you can see certainly why there would be an enhanced threat for severe weather in parts of the central United States. But again, there's still a lot of uncertainty in this impact. And finally, one other thing is lightning and fire, which is very relevant right now across the West, is that this particular study did show a relationship statistically significant for lightning strikes. And of course, that's important for potentially starting wildfires in the West and by phase and for the June through September period. And what they basically showed most importantly was this tendency in phases 6, 7, and 8. Again, these are RMM phases, where you would have this tendency for an enhanced chances for lightning strikes or lightning frequency, as shown in this study, that would generally shift northward over time from the southwest through the Great Basin into parts of the northern Rockies and northern Great Basin during that period, and that would continue somewhat into phase 1, and then the other phases are shown there as well. So kind of in a summary for all the impacts, as I know I'm running out of time, is that what we talk about is here we use the MJO for assessment of upcoming potential pattern changes, more now in the week 3 and 4 period, or week 2 to 4 period, than say a number of years ago, 10 years ago, where it was considered in week 2. So the models have improved in that area. Also for forecasters, model forecast pattern evaluation and weighting. When some of the model forecast spread is quite large, the MJO can help the forecasters out with respect to the forecast that may be most consistent with the pattern of anomalous tropical convection if the MJO is present or active. And also, we do know from the literature that when the MJO isn't active, there's just a general tendency for enhanced odds of extreme events of all kinds because of the dispersion and the amplification of the pattern that the MJO will produce from the tropical heating into the mid-latitudes. And also what we've seen is that the extratropical teleconnection, or the strength of those changes, tends to be strongest for more slower MJO events. For example, in that plot that I showed with different dynamo periods, the one that was a little bit more slower in dynamo period 3 or DP3 on that particular figure, those tend to have more of a, typically tend to have more of an impact to the higher latitudes because they have more residence time in the tropics to potentially impact the circulation in the tropics, then eventually to the higher latitudes. And just to wrap up real quickly, is that for folks who want to know more information about this or keep this up, stay up to date on the MJO, we produce a MJO weekly update that's released at about 4 p.m. Eastern time on our website each week. These are a few examples of some of the information, and it basically includes a lot of the monitoring and prediction products I showed here. Gives an ultimate assessment, an outlook for the MJO strength, phase, and potential impacts in a somewhat compact form that can be used in presentations or other reasons. And again, as I mentioned, it's released. We'll talk more about some of the tools next month on that. And also the MJO impacts and tools go into our operational assessment for the week 1 to 2 global tropics hazards outlook that's produced, which combines all types of variability from the ENSO timescale to the MJO to other faster moving waves that I talked about earlier on in the presentation to produce a map like this for, again, for week 1 and week 2. There's a forecast discussion that goes along with it, and some of the output files are available in various formats, shape files for GIS and also Google Earth formats, and they display the moderate or high confidence for potential tropical cyclone formation and or above or below average rainfall and temperatures, for example, are shown on this particular example. And so along with that at 2:30 Eastern time, we also have a live briefing where we release the new product. We review the recent weather and climate conditions in the tropics. We discuss the major climate variability or rationale for the forecast, to the main players from ENSO to monsoon systems, tropical cyclones. We give an overview of the current outlook, as I mentioned, and any impacts to the U.S. and of course across the tropics. And again, it's an opportunity for you in Google Meet format to ask any questions that you have about the outlook or in general. And it's a pretty short briefing on the order of about 15 to 20 minutes. And some information sources that I talked about already. And that's all I have. I want to thank you for your attention. I'm sorry for going a little bit over. Be happy to take any questions that anyone has. Thank you very much for your time.
Thanks, John, for the presentation. It was quite excellent. If you have a question, go ahead and put that in the chat now, and Jim Z, who's moderating for us, will share them. And while folks are doing that, John, I'll have a quick question for you. With the RMM diagram, can you speak as to how on occasion non-MJO related convection can skew interpretation of the diagram, make it hard to pick out what convective elements are important?
Yeah, absolutely. Great question, Ray. So there's two factors to that. One, I'll take the longer term first, is that one of the things that is done in the methodology that I didn't go over in projecting those daily data onto the index to produce, given points, is that you want to remove the lower frequency. And what I mean by that is any ENSO variability, because you're focusing more on the subseasonal. So there's a 120-day mean that's taken out, averaged out. And sometimes in transition periods, going in and out of ENSO phases, whether it be La Niña or El Niño, a lot of that variability can be aliased. And so you'll see a switch or a shift, if you will, and a lot of the points to the right or to the left or to the up top or bottom, depending on where you're at in that 120 days. Once you get through 120 days, you'll kind of remove whatever ENSO variability is in there, but you kind of have to go into that period. So that's the longer time period. The other aspect is what you alluded to, is that a lot of the other that I really didn't go into, coherent variability that acts on a different time scale, faster than the NGO, such as atmospheric Kelvin waves or equatorial Razi waves. They also have a signal, of course, in the system, both in winds and OLR. And so sometimes those can project, that data will project onto that index such that those points, for example, will be very, very far spaced apart, in an example of a atmospheric Kelvin wave projecting. And so it can fool people in thinking that that's a more of a larger scale MJO event that's moving very quickly, when it's really something that may only last for maybe 5 or 10 days and then all of a sudden stop. And so that data, those type of modes, if you will, or types of variability can get aliased into the plots. And also you'll notice sometimes the plots will instead of going east, meaning in the counterclockwise movement, will sometimes actually go the other way around, even during an MJO event. And that's because some of the equatorial Razi waves, which move west, will project onto that index as well. And so you kind of, that's why I was saying, you kind of have to look at that whole overall envelope over several days, multiple days, to get a feel whether the MJO is evolving as you would expect, or decaying, or so on. I hope that answers your question.
Yep, exactly, John. Thanks. Jim, do you have any?
Only one question has come in so far, and it is, what is the Google Meet address for the weekly update?
I don't have that right here, but I can certainly send that out. It's I have to send it to. We have a list that's sent out each week that if that person can follow up with me, I can add them to that list, which sends out that Google Meet address and phone number.
And that's all the questions we have.
All right. Well, thanks, John. I think we've learned there's a lot to unpack with the MJO there, not only what goes on in the tropics, but how it interacts with our mid-latitude weather. Lots of interesting facets, and we look forward to your presentation next month, where you can build off of this and discuss things some more. So thanks, folks, for attending this afternoon or morning, depending on the time in your area. If you can, if there are others in your office, please let them know that the recording will be made available, and we'll get that link out as soon as it's posted. Thanks for attending, and thanks, John, for presenting.
Oh, you're welcome. Thank you, Ray, and everyone for attending. Take care. Bye-bye.